Hello everyone. So today we're going to be deriving the evidence lower bound loss function, or the ELBO loss function, which is used with variational which is the loss function that's used with variational autoencoders. So effectively, the ELBO loss function has two terms: the reconstruction term and the regularization term, as you see here. Right? The whole idea with a variational autoencoder is that it behaves like an autoencoder, but you're able to generate or sample new points from it because its variance isn't collapsed to zero. It has variance. It has a probabilistic aspect to it. And so this is reflected in our loss function, where we see this first term, the reconstruction term, is very similar to what you might see with an autoencoder. It's just the the expected log likelihood, and then but then we have this new regularization term, which is uses Kullback divergence, KL divergence, which is just a type of measure used to describe the similarity between two different probability distributions. In fact, if you look at the formula for the Kullback divergence, it'd be equal to here, wait, hold up. Like the Kullback divergence of P of x, Q of x is equal to the expected value of the expected log likelihood P of x divided by Q of x. So you can imagine how this can be used to compare the similarity between two different probability distributions, where if P of x and Q of x are exactly the same, this simplifies to 1, log of 1 is 0, so the expected value is 0, which makes sense. It equals 0 when they're the exact same distribution, and it grows larger and larger as the more different they get. And so you can imagine that this regularization term drags down the value of the loss function, prevents you from maximizing the loss function from prevents you from optimizing your loss function because it will be very large if they're very different distributions. And so with our ELBO loss, just to define some of the distributions here, p theta of x given z is our decoder, right? It's the decoder half of our network. And so all this reconstruction term is doing is saying, okay, sample from all the points in our q phi of z given x distribution, which is just our encoder, right? Sample from that and use that value, put it into the decoder, and see what the expected value is, which just describes reconstruction. On the other hand, that defines the probabilistic distribution for our encoder and our decoder, and then P of z is just our prior distribution, which has the form of a Gaussian with mean 0 and standard deviation 1, or using the identity matrix here, right? And the idea is that we want our encoder to be as similar to this normal distribution so that we can effectively continue to capture its probabilistic nature. So that's exactly kind of like the push-pull effect happening here, where the reconstruction term is meant to just calculate how effectively does our encoder-decoder network reconstruct different inputs to their outputs, and the regularization term just continues to capture, well, how much variance do we still have? Are we still how similar to this distribution, this sample distribution are we? So we're going to focus specifically on the Kullback divergence, DKL, and we're going to DKL, and we'll note the fact that both the decoder and the encoder here are normal distributions with some mean. So this is mu of phi of x and some variance function, which is mu of phi squared x times the identity, and similar for the decoder. And so before we can simplify the Kullback divergence term, we need to find what is the Kullback divergence for two different normal distributions. So mu of 1 sigma 1 squared. Here, wait, hold up. Mu of 1 sigma 1, capture the first normal distribution, and mu of 2 sigma sub 2. Cool. So so in deriving this, so as I showed previously, this is the formula for the Kullback divergence, and so we can write this as the expected log of our first normal distribution. So right now what we're doing, just to clarify, is we're calculating the Kullback divergence for two different Gaussians, two different multivariate normal distributions, because of course our encoder and our prior are just two different multivariate normal distributions, so we'll just use this to calculate that. Now from here, the log, so a normal distribution, if I have like a generic one like this, is 1 over the square root of 2 pi to the k times the determinant or the magnitude of sigma, and then the exponential raised to the minus 1/2 x minus mu transpose sigma x minus mu. And so this is our normal distribution. And so you can imagine we take the log of this, we'll get one term, which is k over 2 natural log of 2 pi minus, and then minus in front of that, minus 1/2 the natural log of the determinant of our sigma term, sigma 1, minus 1, or plus 1, minus 1/2 x minus mu sub 1. It's because the natural log of the exponential, those cancel, leaving us with sigma sub 1 minus 1 x minus mu sub 1, like this. Yeah, and then from here, and we can, similarly write for our other multivariate distribution. I will copy this over here. It would just be change this to a plus, change this to a plus, change this to a plus, and then this is a 2, this is a 2, this is a 2, and this is a 2. Oh, there's a minus 1 here. Yeah, immediately we see that these terms cancel, and this becomes, we can actually also factor out the 1/2 term, leaving us with a natural log of the determinant of sigma 2 over sigma 1. Remember, and we're still taking the expectation of this. And then we have these two terms here, minus 1/2 x minus mu 1 transpose like this, and we have this other term here. So I'll just copy those over. And then minus sign here. Okay, so yeah, what's the next step? Well, here's the thing, right? We're taking the expectation, over x and over x over the distribution of p of x. And so here this simplifies very nicely. It just becomes it just becomes sorry, one sec. If we look back here, which is p of x, which is our normal distribution, if you remember above, u sub 1, x sub 1. So this term, the expectation of this value is just this value itself because it's a constant. So we just write, we can take this out. We can say the natural log of the determinant sigma 2 over the determinant sigma 1. I should, since we factored these out, these aren't here. So this simplifies actually really nicely because we can just rewrite this as sigma 1 minus 1, and then this is just the covariance matrix x minus mu 1 transpose x minus mu 1. So we just get this expression, which just simplifies to k, where k is whatever number of dimensions this is, right? And so that simplifies very nicely. And then this other term, but the thing is, this other term, this mu 2, is different from mu 1. So we need to do a transformation where we rewrite this as like this. This is a 1, u2 like that, right? We haven't changed the value of anything here, but what this allows us to do is then we can simplify, so we can gather the terms here, and we can take the terms out from here. And this gives us two expressions. So this simplified to minus k, then we'll get another term which is plus, sigma 1, sigma 2, minus 1, sigma 1. And then we'll get another term which is plus mu sub 1 minus mu sub 2 transpose sigma 2 minus 1 mu sub 1 minus mu sub 2. And so here we see, so we have these four terms that describe our one second. And then we take the that describe our Kullback divergence. Note that we have to, that because we took the expectation value, we need to take the trace of this. But so here's the interesting part about this, right? So the trace of sigma 2 minus 1, sigma 1, if you're not familiar with this, this describes the volume of the ellipsoid around the first standard deviation of our multivariate Gaussian, right? So if you have like a Gaussian like this, and this is one standard deviation, it describes this area, or in 3D like that volume. And so we subtract this from the number of dimensions. This kind of tells us essentially what the how the shape of our like this describes the ratio between the two different probability distributions and in terms of their volume, and this describes how similar the variances of the two distributions are in terms of their orientation, if that makes sense, because that's what the ratio of the determinant tells us. So here we're taking the ratio and then of the two variances and taking the trace of it, and here we're taking the natural log of the two determinants. And then this is something called the Monhobalius metric, which basically describes how far apart two different probability distributions are by taking the difference with respect, subtracting the distance between the two different means, and then multiplying it by the variance of the probability distribution, which is just a metric used to define the distance between two different probability distributions. So effectively, we have a way of our KL divergence for two multivariate normal distributions has one term that describes the volume of the variance, another term that describes the orientation of the variance, and then another term that describes how far away the two distributions are from each other. And so you could see how we can just plug in the values we previously calculated to get the distributions in our VAE to get what the DKL term looks like. And it would be, well, the natural log of, and remember I pulled the 1/2 out of this, so it'd be 1/2 times the natural log of J sigma of x squared plus mu of x. It would be minus because it's in the bottom, plus mu of x, the magnitude of mu of x, just plugging in the terms, plus sigma squared of x, the trace of that, which is just the the trace of this, which would just be the magnitude of it, summing over all the different j values, and then minus k, that doesn't change, and then plus the natural, or I guess I wrote it over there, but yeah, plus the natural log. Yeah, and so this describes our Kullback divergence for the ELBO loss function. Thank you so much for watching.